everyone. I Pritha Gupta welcome you all to the Swayam online course on basic principles of energy management and energy audit. In this course, I will be dealing with the topic renewable energy sources. In continuation with the series, today we are going to learn about the hydropower energy, fuel cells and energy from waste. Hydropower, also known as hydroelectric power, is a renewable energy source that generates electricity by harnessing the energy of flowing or falling water. It has been used for centuries and is still a significant source of electricity worldwide. 25% of electricity generation capacity in world is provided by hydropower plant. In countries like Norway, 99% electricity is produced by hydropower plant. 4% of the total hydel energy potential in the world is in India. In India, 25.32% of total electricity generation capacity is produced by hydel power plant. As per records of Central Electricity Authority (CEA), 46,000 megawatt electricity was generated by hydel power plant in India today. It is increasing day by day because of the institutes like National Hydropower Corporation Limited, that is NHPCL. The kinetic energy of the falling water is used to turn turbine, which turns a metal shaft of an electric generator which generate electricity. For hydropower station, factors like rainfall, steam flow available, head and storage facilities are to be studied. Hydropower projects serve several important purposes and their primary goal is to generate electricity by harnessing the energy of flowing or falling water. However, the benefits and purposes of hydropower projects extend beyond electricity generation and they can vary depending upon the specific project and its design. Here are the primary purposes of hydropower projects. Number 1, for irrigation and agriculture. Water released from hydropower reservoirs can be used for irrigation in agriculture, which is vital for increasing crop fields and ensuring food security in many regions. Second, for recreation and tourism. Hydropower projects, especially those with reservoirs, often create recreational opportunities such as boating, fishing, swimming and camping. These activities can contribute to local tourism and economic development. Third, for flood control. Large dams used in hydropower projects can help regulate river flow and reduce the risk of downstream flooding during periods of heavy rainfall or snow melt. By controlling water release, dams can manage river flow to protect communities and agricultural land. Fourth, for civil water supply. Hydropower reservoirs can also serve as a source of fresh water for municipal, industrial and agricultural purposes. Water stored in reservoirs can be released as needed for various non-power related uses. Next, for generation of electricity. The primary purpose of the most hydropower projects is to produce electricity. Water flowing through the turbines in dams or run of the river systems generates mechanical energy, which is then converted into electrical energy. This electricity can be used to power homes, businesses, industries and public infrastructure. It is important to note that the specific purpose and benefits of hydropower project can vary depending on its location, design and intended use. Additionally, the development of hydropower projects can often involve careful consideration of environmental and social factors to minimize adverse impacts on ecosystems and local communities. The basic elements of a hydropower plant include: number 1, water source. The heart of any hydropower plant is a reliable source of water. This source can be a river, stream or even a man-made reservoir created by a dam. The availability and flow rate of water are crucial factors in determining the plant's electricity generation capacity. Second, Dam or diversion structure. In many hydropower plants, a dam is constructed across a river to create a reservoir. The dam controls the flow of water, allowing it to be released in a controlled manner to generate electricity. In run-of-the-river systems, a diversion structure directs a portion of the river's flow through the power plant without the need for a dam. Penstock. The penstock is a large pipe or conduct that carries water from the reservoir or diversion structure to the turbines. The pressure and flow of water in the penstock provide the energy needed to turn the turbines. Fourth, turbines. Turbines are the key mechanical components of a hydropower plant. Water from the penstock is directed onto the blades of the turbines, causing them to spin. The kinetic energy of the moving water is converted into mechanical energy in the form of turbine rotation. Generator. The mechanical energy produced by the turbines is transferred to a generator. The generator contains coils of wire within a magnetic field. As a turbine spin, they turn the generator's rotor, creating an electromagnetic field that induces an electric current in the wire coils. This electric current is then the electricity generated by the plant. Transformer. The electricity produced by the generator is typically in the form of low voltage alternating current. Transformers are used to step up the voltage to a higher level for efficient long distance transmission. Transmission lines. Once the voltage is stepped up, the electricity is transmitted through high voltage transmission lines to substations and then distributed to homes, businesses and industries. Control systems. Hydropower plants are equipped with control systems that monitor and regulate the flow of water, the speed of the turbines and other operational parameters. These systems ensure that the plant operates efficiently and safely. The specific design and scale of a hydropower plant can vary widely from a small run-of-the-river projects to large multipurpose dams. Hydropower plants can be classified into several different categories based on various factors including their size, operation and purpose. Here is a detailed classification of hydropower plants. Number 1. Based on size and capacity, classified into 3 to 4 categories. Large hydro, exceeding 100 megawatt and usually feeding into a large grid. Medium hydro, 15 to 100 megawatt usually feeding into a grid. Small hydro, 1 to 15 megawatt usually feeding into a grid. Mini hydro, 100 kilowatt to 1 megawatt either isolated or feeding into a grid. Micro hydro, 5 kilowatt to 100 kilowatt usually provides power for a small community or rural industry in remote areas away from the grid. Pico hydro, from few hundred watts up to 5 kilowatts. Next, based on the operation, hydropower plants are of run-of-the-river power plants without pondage. These plants do not have large reservoirs or dams. They divert a portion of the river's flow through a canal or a penstock to utilize the natural flow of the river to generate electricity. Second, run-of-the-river power plants with pondage. The above plant has some limitations. To overcome this drawback, in this type of hydroelectric plant, the available water from river or lake is stored in pond. Due to this storage water in pond, it is useful to run the plant during off-peak and peak period. The capacity of such type of hydroelectric plant depends upon the size of pond. Storage hydropower plants. These plants have a dam and a reservoir to store water. They can control the release of water to generate electricity, providing flexibility to meet varying demand. Pumped storage hydropower plants. These plants have two reservoirs, one at a higher elevation and one at a lower elevation. They can store excess energy by pumping water from the lower reservoir to the upper reservoir during periods of low demand and generate electricity by releasing water from the upper reservoir to the lower reservoir during peak demand. Next, based on purpose. Single purpose hydropower plants. These plants are designed solely for the electricity generation. They don't have other primary purposes like flood control, irrigation or water supply. Multi-purpose hydropower plants. These plants serve multi-purposes in addition to electricity generation. Common secondary purposes include flood control, irrigation, water supply and recreation. Multi-purpose dams are often found in large multi-use projects. Next, based on location, high-head hydropower plants. These plants are located in areas with a significant difference in elevation between the reservoir and the turbines, allowing for efficient energy conversion. They are typically run off the river or have relatively small dams. Medium head hydropower plants. Medium head plants have a moderate elevation difference between the water source and turbines, typically falling with a range that allows for efficient energy conversion without the need for extremely high dams or massive reservoirs. The exact head height can vary depending on the specific plant and its design. Low head hydropower plants. These plants are located in areas with minimal elevation differences. So, they require a large flow of water to generate the same amount of electricity. They are often used in river systems with relatively flat terrain. These classifications help differentiate hydropower plants based on various criteria, enabling planners and policy makers to consider the specific needs and environmental considerations of each type when developing energy projects. The amount of electricity that can be generated by a hydropower plant depends on two factors. Number one, flow rate, the quantity of water flowing in a given time, and second, head, the height from which the water falls. The greater the flow and head, the more electricity produced. As flow rate equals the quantity of water flowing and head equals the height from which water flows. The power generated in a hydropower plant can be calculated using the following formula: P equals eta into rho into G into Q into H, where P is the power generated in watts or kilowatts, eta is the overall efficiency of the hydropower systems expressed as a decimal, for example 0.85 for 85% efficiency. Rho is the density of water, typically around 1000 kg per meter cube. G is the acceleration due to gravity, approximately 9.8 meter per second square. Q is the flow rate of water in meter cube per second. H is the head height, which is a vertical distance between the water source such as a reservoir or dam and the turbines measured in meters. So, this is all about the basics of hydropower energy. Now, let us move ahead and learn about the fuel cell. Fuel cell is an electrochemical device that converts the chemical energy of a fuel and an oxidizing agent, usually hydrogen and oxygen, directly into electrical energy, heat and water without the need for combustion. It operates on the principles of electrochemistry and is a highly efficient and clean energy conversion technology. Fuel cells are different from batteries in that they require a continuous source of fuel and oxygen or air to sustain the chemical reaction. There are many types of fuel cells, but they all consist of an anode, a cathode and an electrolyte that allows charges to move between the two sides of the fuel cell. Fuel cells are used for primary and backup power for commercial, industrial and residential buildings and in remote or inaccessible areas. They are also used to power fuel cell vehicles including forklifts, automobiles, buses, boats, motorcycles and submarines. The operation of a fuel cell involves converting the chemical energy of a fuel and an oxidizing agent into electrical energy through an electrochemical process. The main components of a basic fuel cell includes number 1 anode. The anode is a negative electrode typically made of a porous conductive material, often carbon based, coated with a catalyst. It is where the fuel is supplied and where the electrochemical oxidation reaction takes place. Second, cathode. The cathode is a positive electrode also made of a porous conductive material coated with a different catalyst. It is where the oxidizing agent, usually oxygen or air, is supplied and the electrochemical reduction reaction takes place. Third, electrolyte. The electrolyte is a material that separates the anode and cathode. It is often an ion conductive substance such as a solid oxide or a proton exchange membrane (PEM), depending on the type of fuel cell. The electrolyte allows a migration of ions but prevents the flow of electrons. Operation of a basic fuel cell. Hydrogen gas is typically used as a fuel in a basic fuel cell. The fuel is supplied to the anode. Oxygen gas from the air is supplied to the cathode. In some fuel cell types, air is used directly, while in others, purified oxygen is supplied. At the anode, hydrogen gas split into protons and electrons in the presence of anode catalyst. This reaction can be represented as H2 gives 2H plus 2 electrons. At the cathode, oxygen molecules O2 react with protons and electrons from the anode to form water H2O. This reaction can be represented as half of O2 plus 2H plus 2 electrons gives H2O. Electrons produced at the anode cannot pass through the electrolyte. Instead, they flow through an external electrical circuit, creating an electric current that can be used to power electrical devices or perform other work. The protons generated at the anode migrate through the electrolyte to reach the cathode. This movement of protons constitutes an ionic current. At the cathode, protons from the anode side combine with electrons from the external circuit and oxygen to form water molecules. Fuel cells also produce heat as a byproduct of the electrochemical reactions, which can be harnessed for various purposes such as heating water or space. The only waste products produced by the basic fuel cell are water vapor and heat. There are no harmful emissions, making it an environmental friendly energy conversion technology. Basic fuel cells can operate continuously as long as a supply of hydrogen fuel and oxygen or air is maintained. They offer high efficiency, low emission and a potential for a wide range of applications. The operation of basic fuel cell is highly efficient and clean, making it a promising technology for the various sectors including transportation, stationary power generation and portable electronics. Here is a table summarizing some key types of fuel cells. Fuel cell type, electrolyte, operating temperature range, anode, cathode and its applications. The first fuel cell type called as solid oxide fuel cell, SOFC. Solid ceramic electrolyte is used as an electrolyte. It is used at high temperatures of 800 to 1000 degrees Celsius. Hydrogen, natural gas, methane or others are used as fuel in anode, whereas oxygen or air is used as oxidizer in cathode. They are used for stationary power generations, industrial applications. Next, alkaline fuel cell, AFC. Alkaline is used as electrolyte. It works at a moderate temperature of 50 to 250 degrees Celsius. Hydrogen, usually in pure form, is used as anode and oxygen from air is used as oxidizer as cathode. Space mission specialized applications are its applications. Phosphoric acid fuel cell, PAFC. Phosphoric acid is used as electrolyte. It again works at a moderate temperature of 150 to 220 degrees Celsius. Hydrogen as used as fuel, anode, and oxygen from air as oxidizer, cathode. Distributed generation, combined heat and power are some of its applications. Molten carbonate fuel cell. Molten carbonate is used as electrolyte. It works at a high temperature of 600 to 700 degrees Celsius. Hydrogen, natural gas, methane or others are used as fuel in anode, whereas oxygen or air is used as oxidizer in cathode. They have a wide applications in large scale power generation, industrial cogeneration. Direct methanol fuel cell, DMFC. In this, polymer membrane is used as electrolyte, operates in the range from 60 degrees Celsius to 130 degrees Celsius. Methanol is used as fuel in anode, whereas oxygen is used as oxidizer in cathode. DMFC, direct methanol fuel cells, are convenient for portable power applications with outputs generally less than 250 watt. Advantages of fuel cells. High efficiency. Fuel cells are highly efficient at converting the chemical energy of fuels into electricity, often surpassing traditional combustion based power generation methods. Second, low emissions. Fuel cell produce minimal harmful emissions. Hydrogen fuel cells in particular emit only water vapor and heat as byproducts. Third, quiet operation. Fuel cells operate quietly since they lack moving parts, making them suitable for noise sensitive environments. Reduced greenhouse gas emissions. When powered by hydrogen produced from renewable sources, fuel cells can contribute to a significant reduction in greenhouse gas emissions. Scalability. Fuel cells can be scaled to meet a wide range of power requirements, from small portable devices to large scale power plants. Reliability. Fuel cells have a long operation life and high reliability, especially when used in stationary power generation applications. Next, disadvantages of fuel cells. High initial cost. Fuel cell systems can be expensive to manufacture and install, primarily due to the cost of materials such as platinum used in catalyst. Limited fuel infrastructure. The infrastructure for producing, storing and distributing hydrogen fuel is underdeveloped in many regions, which can limit the widespread adoption of fuel cell technology. Fuel storage and transportation. Hydrogen, one of the common fuel sources for fuel cells, has low energy density by volume, requiring high pressure storage or cryogenic conditions for transportation and storage. Sensitivity to impurities. Fuel cells are sensitive to impurities and require high pure fuel and oxidizer sources. Operating temperature. Some types of fuel cells such as solid oxide fuel cell, SOFC, operate at high temperatures, which can result in longer startup times and materials challenges. Applications of fuel cells. Transportation. Fuel cells are used in hydrogen fuel cell vehicles and buses, providing zero emission transportation options. Stationary power generation. Fuel cells are used for backup power systems in buildings as well as for distributed power generation, including residential and industrial applications. Portable electronics. Small, lightweight fuel cells power portable electronic devices like laptops, smartphones and drones. Material handling. Hydrogen fuel cells are used in forklifts and other material handling equipment in warehouses and distribution centers. Combined heat and power. Some fuel cells like phosphoric acid fuel cells PAFC are used in combined heat and power systems to simultaneously generate electricity and useful heat for heating or cooling buildings. Backup power. Fuel cells provide reliable backup power for critical facilities like hospitals, data centers and telecommunications infrastructures. The choice of fuel cell and application demands on factors such as efficiency requirements, available infrastructure, operating conditions and cost considerations. As fuel cell technology continues to advance, it is expected to find broader and more diverse applications in the near future. Energy from waste refers to the process of generating electricity, typically in the form of electricity or heat, by using various technologies to convert waste materials into usable energy. This approach serves two main purposes: reducing the volume of the waste sent to landfills and generating renewable energy. Here are some common methods and technologies used to extract energy from the waste. Number 1, incineration. Incineration involves burning solid waste at high temperatures in controlled environments. The heat generated during combustion can be used to produce steam, which drives turbines to generate electricity. Incineration also reduces the volume of waste by up to 90%, making it less harmful for disposal. Anaerobic digestion. Anaerobic digestion is a biological process that breaks down organic waste such as food scraps and sewage sludge in the absence of oxygen. This produces biogas, which is primarily composed of methane and carbon dioxide. Biogas can be used for electricity generation or as a source of renewable natural gas. Next, landfill gas recovery. Landfills emit methane, a potent greenhouse gas, as organic waste decomposes. Methane can be captured and used as a source of energy through landfill gas recovery systems. This methane can be used for electricity generation or as a renewable natural gas. Waste to energy plants. Waste to energy plants are facilities designed to burn municipal solid waste to generate electricity and heat. These plants are equipped with advanced pollution control technologies to minimize emissions. Pyrolysis and gasification. Pyrolysis and gasification are thermal conversion processes that heat waste materials in the absence of oxygen. These processes can produce synth gases which can be used for electricity generation or as a feedstock for producing chemicals and fuels. Plasma gasification. Plasma gasification uses extremely high temperatures generated by plasma torches to break down waste materials into syngases and as a vertified slug. This process is capable of handling various types of waste including hazardous materials. Combined heat and power systems. Some waste to energy plants incorporate combined heat and power systems which simultaneously produce electricity and useful thermal energy such as steam or hot water. This improves overall energy efficiency. Energy from waste can help reduce the environmental impact of waste disposal and contribute to the generation of renewable energy. However, it is essential to address environmental concerns such as emissions and residue management associated with these technologies. Additionally, recycling and waste reduction should remain priorities to minimize the amount of waste that needs to be processed for energy generation. So, with this we came to an end of today's lecture. Thank you for your patience and we will meet in the next lecture. Thank you.